Okay, here we have a potential energy diagram for a carbon-carbon bond. And remember, what goes along the x-axis in these graphs? Tell your partner what goes along the x-axis in these covalent bonding graphs. Yes, I'm loving seeing this. Yes, because it is indeed the internuclear distance. Okay. And what goes up and down? The potential energy. It just says energy, but it really should say the potential energy. Okay. And this is for a carbon-carbon bond. Which of these describes two interacting carbons separated by 0.1 nanometers? So 0.1 nanometers is here. Okay. So the attractions between the atoms are stronger than the repulsions between the atoms. Is that true? Yes.
I watched like one of the videos of the fact that they said that like if it's in like the negative section, then the attraction is stronger than but that's what the video said.
Yeah, on the other hand, you're okay. Okay, well, A is wrong because the internuclear distance won't decrease regardless, right? Because it's not going to get smaller because it's too small right now. Yes? The repulsions between the atoms are stronger than the attractions, and so the internuclear distance will increase. That's probably the correct answer. I understand what you're saying, Tony, but let's just take a look at the other options first, okay? And let's see if this is a good question or a question. Attractions are maximized and repulsions are minimized. Is that true? No, that would happen where? Where are the attractions maximized and the repulsions minimized? That would occur at the X marks the spot. Yes? So this one is a no, that one's a no. There are no attractive or repulsive forces between the atom. Well, that one's a no, so it has to be B. Yeah, I wouldn't get too worked up about it because you can do that one by process of elimination. Yeah. None, the others are completely wrong. Like there's no way the other ones are correct. Okay. Then maybe this is not a good question. Rework this answer. Fix. How's that? Better? Okay. Good stuff. Consider the potential energy curve to the right. Oh yeah, we were just doing number 8. Would we like to go over anything else? 9? Okay. We have BR2. If you were to add this diagram, a similar curve for Cl2, it would feature a potential energy minimum represented by point C. That is it higher and shifted to the left, or is it lower and shifted to the right, or is it the same and shifted to the left? So BR2, BR is below Cl on the periodic table, yes? So what can you say about bond length? Yeah, the bond length of BR2 is greater than the bond length of Cl2. So that means that where do I go from and to measure the bond length? I start at, am I going vertical or am I going horizontal to measure the bond length? Horizontal. And I start at the axis and I go to point C. Whoops. Okay, that right there is the bond length. And because Br is a larger atom than Cl, because it has more, why is Br bigger than Cl? It has more occupied shells, okay? And so that's why the bond length of Br2 is longer than the bond length of Cl. There's simply more space in between them because the atoms are bigger. And in terms of bond strength, as bond length increases, what happens to the bond strength? Talk about that with your partner. As bond length increases, bond strength decreases. If you have trouble remembering that, think about trying to break a pencil. Okay, what if you've got like a little stub of a pencil? Is that easier or harder to break? Harder to break, yes. But if you've got a long pencil, easier to break. Have you ever tried breaking like a little tiny stub of a pencil? It's really difficult. It's not a great analogy. Like it's not the length that makes it. It's not an analogy, it's just a way of remembering it. Yes? Okay. What you can think of is that if we had ClCl, and we've got our nucleus and our nucleus, and we've got our shared electrons in between. Maybe I should draw them in between. And if I have Br is bigger. So its nuclei are further from the shared electrons on average. Does that make sense? And so if the distance is greater, the strength is, the coulombic attraction is smaller. And so the bond energy of bromine is going to be smaller than the bond energy of chlorine. And if the bond energy is smaller, where do we start and where do we end on the graph to measure the bond energy? We start at the x-axis and we measure down to measure the bond. I don't know, it sounds like... Okay, so the bond length should be longer for Br. So the point C should be shifted to the... Oh yeah, it's because we now have Cl. So Cl is smaller, so the point C should be shifted to the left. Yes? Okay, and should it be higher or lower for Cl?
It should be lower, right? So it takes more energy.
Cl is a stronger. The bond energy. Cl is. So the bond energy is greater, and so the point should be lower because you're saying how much energy does it take to get out of that pit?
Well, the answer he said was A.
Did it? The answer key is wrong. Fix key should be A. No, not A. C. Okay, is that better? There we go. Why is it lower? Because if I have it lower, then my bond energy will be greater. And chlorine has a stronger attraction. Fc is greater for Cl. Therefore, the bond energy is greater. So this is the potential energy. They call things potential energy wells. How much energy is it going to take to break that bond? You have to get it all the way from being completely stable to being broken. So you have to put in enough energy to take it from its most stable state to being broken. Up here. That makes sense? Cool. Okay. What else we got? Anything else from here? Yes. 12. The plot to the right shows the potential energy curve of two diatomic molecules, AB and CD. Which of the following is true? I'm just going to draw in a little line here. If I can, it won't seem to let me. There we go. Okay. CD has a stronger bond. First of all, this one is CD. This one is AB. Who has the stronger bond of those two? Tell your partner, who has the stronger bond? So CD is we're going to require more or less energy to break. More. Okay, that's this one here. CD requires more energy to break. That line there, that gives us our bond energy. And therefore, is the CD bond stronger or weaker than AB? Therefore, CD is stronger than AB. So we're either, this one is good here, this one is wrong because CD is not weaker. CD has a shorter bond. Is that true? Does CD have a shorter bond? Yes, because we have CD bond length. Whoops. That's shorter than the AB bond length. So this is true and this is true. And is it true that CD has a stronger bond because it has a lower minimum energy than AB? Is that true? I think so. Sounds true to me. Lower minimum energy, stronger bond. I think so. Yeah? Does CD have a shorter bond length because its energy minimum is at a shorter internuclear distance than AB? Is that true? It sounds true to me. What does the answer key say?
There is no answer key.
Oh, that's fantastic. Okay, so I would say both A and C. And I'm going to change this to is, are, true. Fix. Okay, so it's going to be A and C. Were there any others that were missing answers? Or just 12? Okay, good. Did we have any questions from our bond orders and bond energies? If you had any problems with some of the questions, you might need to say, for example, this one, number 5, you would need to make sure you drew the actual Lewis structures because these are just the skeleton structures which show the bonds, bond locations, but they don't tell you if it's a double bond or a single bond. So you would need to then draw the Lewis structure. Now, what is step 1 of drawing a Lewis structure? Tell your partner, what is step 1? Count the valence electrons. Number 2 is draw the skeleton. And so we have a skeleton here. We're going to do this one. So our valence electrons for H2C, H2CO is, we have 1 plus 1, right? Wow, what is wrong with me? 2 times 1, that's better. Plus, how many does carbon have? Group 14 it has 4. Oxygen is group 16, it has 6. So in all we have 12 electrons. So if we were to do that, here we have our skeleton structure, and then we have add, what do we add? Lone pairs. Until what? Until every atom has an octet or 8. Except for exceptions, of course, okay? So who does not have 8 in our structure here? H doesn't have 8, but does it need 8? No, it's an exception. It only needs 2. Does carbon have 8? No, it only has 2, 4, 6. So I'm going to put on a lone pair that makes 8. Does oxygen have 8? No. So I'm going to add, it's got 2 already, 4, 6, 8. Now, if there were 3 steps, we would be done, but there's not 3 steps, there's more than 3 steps. What do we do after step 3? We count the electrons in the structure. So how many do we have? Every line counts for 2. Every set of dots counts for 2. So we have 2, 4, 6, 8, 10, 12, 14 electrons. What do we do with that number?
Check it.
We check it. We take that 14 electrons and we compare it to our 12 electrons. And we say we have 1 pair too many. And if we have 1 pair too many, what do we do? If there's too many, you have to get rid of some. Yes, too many, get rid of some. How do we get rid of when we're drawing things? We erase. How many do we need to erase? We have 1 pair too many. How many pairs do we have to erase? 2 electrons or 1 pair. We have 1 pair too many, so we're going to erase 1 pair, which is 2 electrons, okay? Where do we erase them from? The central atom. Who is our central atom? Carbon. Okay, so here's our carbon. And we say, okay, I'm going to erase those electrons there. Now they're gone. Now I don't have 14 electrons. Now I have 12 electrons. Am I good now for my number of electrons? "12 and 12, that's good. And if I left the structure like this, what would be wrong with it? Tell your partner, what would be wrong with this structure if I left it like this? Carbon has only 6 electrons, and that's a problem. You can never have carbon with 6 electrons. Who should have 6 electrons? There's 2 of them. B and aluminum, boron and aluminum, but only those 2. So most of the time, almost all the time, you're looking for 8. That does not have 8. How could we help carbon who has only 8? We could double bond. We could take this lone pair here and move it in here. Okay, so instead of having that, we would have C double bond O. We still have a lone pair and a lone pair. You can put those wherever you want them. B ball. Beryllium, boron, and aluminum. Those are your exceptions. Yep. And hydrogen, yeah. Okay, and that is your structure. Okay. This other one, we're not going to go through the whole Lewis dot structure process, but what I'll do is I'll just throw in my lone pairs there. That's the correct structure. There's no double bonding, no nothing. So if we compare our CO bond in CH2O and our CO bond in methanol, if we compare those 2 green bonds, which will take more energy to break? The 2 bonds. Double bonds are always stronger than single bonds. Triple bonds are always stronger than double bonds. So, do you see how you have to have your Lewis structure to be able to say, do I have a single bond? Do I have a double bond? Yeah? And similarly, when you get down to here and you're like, how do I tell which of these two has the stronger bonds? How could you tell? You would have to draw the Lewis structures. Yeah? And you would say, okay, N.
All ones with H, you can just check for bond.
All the ones with H, you can just check for bond length because they're all single bonds. Okay? Because CH is going to be a single bond. SIH is going to be a single bond. If it's H, it's always a single bond, so you don't have to worry. But if you've got N and 2, we have 2 times 5. Right? And so we go, okay, I got an N and an N. And I've got 10 electrons, but let's go 2, 4, 6, 8, 10, 12, 14. I gave everybody 8 electrons. How many electrons is that? 2, 4, 6, 8, 10, 12, 14. So that is 2 pairs too many. Yes? I have 14, but I want 10. So what must I do? I need to erase how many pairs? I have 2 pairs too many, so I'm going to erase 2 pairs. So what that's going to look like is I'm going to have an N and an N, and I'm still going to have these guys here. Because this is diatomic, it doesn't matter which one I erase them from. Normally we would erase from the central atom. There is no central atom you can pick. You could erase them both from one of them and do it like that. Or you could erase from like that. Now you're going to have problems with having the correct number of electrons. Nitrogen over here has only 2, 4, 6 electrons. Nitrogen over here has only 2, 4, 6 electrons. Everybody needs to have 8 electrons. And that's where the next step comes in. And you remember, we've got our 2 pairs. We need to turn, guess how many pairs? 2 lone pairs. So 2 pairs, 2 pairs, 2 pairs, 2 lone pairs into 2 bonding pairs. Yes?
Wait, technically, so you can just erase 2 pairs.
Yeah. Well, yeah. So what you would do is you would say, okay, I'm going to, normally what I would do is I would go and say, okay, I'm going to bring these guys into the middle and make them a bonding pair. And then I have to do that to a second pair, so I'm going to bring these guys into the middle and turn those into a bonding pair. And now if I count my number of electrons, I have 2, 4, 6, 8.
So basically, in total, you erase 4, 1, 2, 3, you erase 4 lone pairs, replace the 4 lone pairs with 2 bonds.
Yeah. Yeah. And as I've mentioned before in the past, sometimes what they'll do is they'll say, instead of saying give everybody 8 electrons, what they'll do is they'll say you can only work with 10 electrons. And if you were to do it that way, you'd be like 2, 4, 6, 8, 10. Uh-oh, I just ran out. Right? That's the other way to go. And then you'd have to say, well, how can I get this poor little nitrogen over here to have enough, I would have to turn those into double bonds. The reason I like erasing is because it tells me how many am I going to have to turn. It tells me if I erase 2 pairs, I have to turn those into bonding. I have to turn 2 lone pairs into 2 bonding pairs. That's why I like the erasing method better. But if you like just doing it, you can do it whatever method you want. Do whatever you like. Yeah? And you can find people all over the internet who will show you the way without erasing. Okay, so if you're interested in that, feel free to go out, just look up things. They're all over. Any other questions on anything? So N2 anyway would have triple bond. O2, if we did the same process, would have a double bond because it's got 2 extra electrons each. Anything else? Yes?
How do you do problem 1 in this shape?
Problem 1 on page 50. Okay, which molecule has the strongest bond between the 2 atoms? OH, HS, HF, HCl, HI. Who can we get rid of immediately? HI. Why? Because I is very big. Which means that our internuclear distance is long bond, and therefore longer bonds are weaker. Yeah? Cl is bigger than F. So if we say, if I'm comparing these 3 here, I can say it's definitely not those 2, right? And now what I'm going to do is I'm going to take a look at these 3 guys because I've got I've got OS, I've got OH and HS, and on my periodic table, here's O and here's S. So this is smaller, this is bigger.
So they're more.
Okay, so I'm going to say, okay, that one, no. And now I'm comparing OH and HF. No. So I look on my periodic table and I say, where are they relative to each other? They are both in the same period. O is here. F is here. And F is smaller. Yes? Why is F smaller than O? Tell your partner. F has more protons. Therefore, Zeph is higher. Yeah? And therefore, FC is greater since Coulombic attraction is proportional to charge. Therefore, fluorines, electrons are pulled in more tightly. is good? Okay, good. So our answer then would be HF. Other questions? Going once, going twice, going 3 times. Sold! Sigma and pi bonds on page 51. Sigma and pi bonds. Okay, a sigma bond. This is the symbol for sigma. Practice writing it a few times. You start here, you go down, you go around, and you go up, and then you go across like this. That is a lowercase sigma. Those are just arrows showing you which direction to write it. Okay, so you go down, up, and across. Down, up, and across. Down, up, and across. So a sigma bond is a covalent bond in which the highest electron density is between the 2 atoms. Where is that? Here. Maybe I'll grab some green. Here. Okay? Where is that? It is along the bond axis. It is along the internuclear axis. So our highest electron density is along the bond axis. Every single bond is a sigma bond. Sigma bonds are single bonds. Actually, no. Single bonds are sigma bonds. Sigma bonds can be part of a double bond also. Okay? The first bond in a double or triple bond is sigma. And when you have a sigma bond, you can have free rotation along the axis. And I'll show you what that means in a second, okay? And what causes a sigma bond to form? You can have an overlapping s orbital with an s orbital. So s plus s. So you have an s orbital, we have an s orbital. They overlap. And when they overlap, we call that a sigma bond. And where are the electrons? They're in between the 2 nuclei. Yes? Okay. You can have an s orbital overlapping a p orbital. So we have an s orbital in hydrogen. Fluorine, if you remember fluorine, we have 1s2, 2s2, 2p, 1, 2, 3, 4, 5. There we go. 2p. And you see how here we have our unpaired electron? That's in a p orbital. Okay, so this is our unpaired electron. That's that one there. It's the one in the 2p. So we get an s orbital overlapping a p orbital. And guess what kind of bond we get? We get a sigma bond. And where are the electrons? The electrons are between the nuclei. We can also have a PP overlap, and this is what we call head-on overlap. We'll look at what happens when you get non-head-on overlap later. Pardon me? These are all sigma bonds, okay? Sigma bond, sigma bond, sigma bond. They're all single bonds. Anytime you have a single bond, it must be a sigma. There's no choice. A single bond is a sigma bond. Okay, so here we have a p orbital plus a p orbital. And we get a, guess what? A sigma bond. And where are the electrons? The electrons are along the internuclear axis. Which is just a different way of saying the electrons are between the nuclei. Yes? Pardon me? Oh, I don't think so. No. Why have I been writing dashes? I don't know. I don't know why I've been writing dashes. They just came out of my pen. There, let's get rid of those because I don't think you need them and I don't think you probably should put them. Yeah, I don't know what was going through my head there, but probably nothing, to be honest. Okay. Now we're going to talk about pi bonds. Okay, and you guys know the symbol for pi. Okay. There's our pi. And a pi bond, it's still a covalent bond, but the density is not along the axis. The density is around. So the density is around the internuclear axis. So here I have my nucleus. Here I have my nucleus. And here I have my electrons. So there's a blob above the axis and a blob below the axis. So the electron cloud for the bond is above and below the axis, the internuclear axis. What do we call an area where there are no electrons? We call it a node. So does this have a node?
Yes.
Yes. Okay, so this here, these two lobes make up one bond. These two lobes together are only one bond. One pi bond. So that's not a double bond on its own. That's just a pi bond. You always get sigma bonds first, and you only get pi bonds after you already have a sigma bond. Pi bonds come after you have a sigma bond. Now, what kind of orbitals give us this above and below the axis kind of density? Well, if we look at a p, once again, we have p and p, but do you remember before they overlapped this way? Head on. Everyone to go like this. Head on. No, not like this. You need to have the two ends of the p orbital. Do you see how we have up here? Come on over. Do you see how we have the two ends of the p orbital? That's your elbow and your fist. Elbow, fist. Elbow, fist. Hi. I want you to write the equation for the second ionization of aluminum. Mm-hmm. If you're stuck, you could write the first ionization of aluminum, and then you could see if you can extrapolate that to the second ionization energy.
Okay.
Okay.
Also, the group is like this. And the group is
Yes. Yes. Good stuff. Okay, so P, when they overlap like this is called head-on overlap. What kind of bond do we form if there's head-on overlap? Sigma. Now, if we have sideways overlap, what kind of bond do we form? Pi. Okay? So if you have a P overlapping with a P, you'll notice that your electron density is here and electron density is here. Yeah. And then we have, what do we have in the middle? We have a node. And what do we have in our pi bond? We have a node along the axis. This is one pi bond.
So that's one pi bond.
That's one pi bond. Each pi bond has two lobes, yes? Are there what? Huh?
So is it like SP? Wait, so is that like SP?
Yes, you do. That's when you get a double bond. A double bond is a sigma bond and a pi bond. Okay? So your sigma bond forms first, and then you get a pi bond.
I think I'm just fine.
Yes. You can never have a pi bond by itself. So, here's the deal. The second and third bonds in a double bond are always pi bonds. Yes?
Pi bond, you have pi bond which is in electron density that already
Yeah. Yeah.
and you sigma bond along with it.
Yeah. Yeah. Hmm? Oh, the node is for the electrons that are in the pi bond cannot go along the internuclear axis. Those are different electrons from the ones that are along the axis. Okay? So we've got two electrons along the axis and we've got two different electrons above and below the axis. And then if we have a triple bond, we not only have above and below the axis. So if this is my axis, I've got along the axis is my sigma. Here's a pi. Where would my other pi bond go? In front and behind. So I'll have a blob along the axis. I'll have a blob up here and a blob down here. That's a second bond. And my third bond is a blob at the back and a blob at the front. I do have some pictures of these later on, so you'll get to see them. Okay? But for now, you just need to be able to count them up. And you say, okay, what have I got here? This is a sigma bond because it is a single bond. A sigma bond plus a pi bond is a double bond. A sigma bond and 2 pi bonds is a triple bond. So a bond always contains a single bond. You might have a pi bond or you might have 2 pi bonds. Yeah? We have free rotation only when we have sigma bonds. I'm going to get you guys some models. I forgot to bring them in today, but we'll let you take a look at those tomorrow, okay? These two guys, double and triple bonds, do not rotate. Ah. Let's see if I've got a video. Double and triple bonds cannot rotate. Single bonds will rotate. Let's see if I can find a little video with that. Rotation, single bond, double bond. Oops. This doesn't look any better than anything I could do. Oh, here we go. Maybe. Or maybe not. I'm going to just get you the models so you can see them tomorrow in person, okay, like in 3D. All right, so let's not worry about that too much right now. If you don't understand why a single bond can rotate and the double bond can't, don't worry about it. We'll get to it tomorrow. So here is a comparison chart. Sigma bonds, head-on overlap. Pi bond, sideways overlap. Sigma, electron density is along the internuclear axis. Pi is around the internuclear axis. Sigma bonds are present in single and double and triple bonds. Pi bonds are present only in double and triple because they're always the second or third bond in a double triple bond. The sigma bond is one of the bonds in a double or triple bond. Pi bonds are the second and third bonds in the double or triple bonds. Okay, here's kind of a picture of the way it rotates. Do you see how you've got like a single, well, maybe I can kind of do it. Okay. So if you look, can I rotate here?
Oh.
Right? Are my hands rotating on this axis? Yes. Okay, rotating, 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 rotating. Now what if I have my hands like this? Can they rotate? No, because these bonds will break, right? Like if I was to actually do this, these pens would eventually break. Yeah? So you have free rotation on a single bond, but not on a double bond because the two of them lock it into place. Okay? So you can see here, both of these are 2 carbon atoms. So you see the F, 2 carbons, carbon, 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 and it has a chlorine atom on it. Chlorine, chlorine. These are the same molecule. All that has happened is that it has rotated. Yeah? Same molecule. Have we talked about isomers?
No.
Okay. Isomers.
Is it like isometric?
Iso means they have the same molecular formula, but different structural formulas.
All numbers.
Isomer. Iso meaning the same. So they have the same molecular formula, but they have different structural formulas. So you might have 2 structures that look slightly different, but if you realize that rotation can occur around this bond, these are actually just exactly the same thing. We've just had rotation around that bond. So those are not isomers. They are the same molecule. That's where they have the same structural formula and the same, these guys have the same structural formula. Same structural formula. If you were to draw a Lewis structure for this, it would be the same for both of them. So let's say I have C, do I have room down here? I do. C, H, 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 C, I'm going to put my fluorine here. What is on the rest of all of those? Those are H's. Do I need to draw all the H's or are you good? We're good? Okay. So I could have my F there. That is the same as C, C, F. Yeah? Which is also the same as C, C, F. In that case, I haven't rotated around the axis. I've actually flipped the whole molecule. The whole molecule has just rotated. Yes? Right? So you can imagine a molecule in space, right? This molecule is the same as this molecule because it is just rotating. Yeah? And this is the same. Oh, I wonder if I could do that. Here, I'm going to put a piece of tape, I think. Oh, I know what I'm going to do. Here we go. This is rotating. Is this the same molecule as this? Right? This is the same molecule as that. It's just rotating. Okay? Hi. Y'all done? Thank you so much. Thank you. Is good? Same molecule, same molecule. Single bonds, that can happen. Double and triple bonds, that cannot happen. You cannot rotate. Okay? And when you have these are all the same as, these are not isomers. They're all the same molecule. They will have all the same chemical properties. They will behave the same chemically, right? They're the same chemical. Now, hold on. If we go over to our double bond, where we do not have free rotation, if I put a fluorine here and here on the same side of the double bond,
Why is this CIS?
huh?
Why is
Cis,
this? Why is that?
because cis essentially means the same. Trans means across. And our two groups of interest, the things that are not hydrogens, are either on the same side or they are across from each other. They're either on the same side or they are across. They are either cis or they are trans. Can you guys show me cis? Trans. Cis. Trans. Cis. Trans. Do you know where the cis transgender things came from? They came from organic chemistry. They really did. Those terms, before they were used for genders, for like decades before anyone used that terminology, cis and trans. I think what happened is that the prefix trans was used for gender all on its own for quite some time. And then probably somebody who had studied chemistry along the way was, well, if you're not trans, then you must be cis. And that's where the cis came from. So I think the trans for transgender would have developed that terminology on its own, separate from chemistry. But I think the terminology cis came from someone saying, well, we have trans in this context and we have trans in that context. Why don't we use cis in this context as well? Which I think is really cool, because I'm a chemistry geek. So yeah, when all that language sort of first became into, super like public use, and they were doing like lots of training for teachers. I've been in the business a long time. I was here when they were all like, ooh, these are new words, you need to learn them, right? Ms. Wu and we were like, we already know these words because we're chemists. So anyway, I don't know, we got really excited about it because we're just dorks, but at any rate, this kind of isomer is called a cis trans isomer, and it only occurs when you have a double bond. It's not going to occur when you have a triple bond, because why won't you have it when you have a triple bond? Because a triple bond gives you what molecular geometry? Gives you linear geometry, whereas this one, what's our geometry here? The geometry is trigonal planar. So it's really that double bond that allows you to have that cis-trans isomerism. Okay? Now here's the tricky bit. And I know I've totally lost you because we only have 5 minutes left. So what I'm going to have you all do is I'm going to have you breathe in and out. Everybody, breathe in. Hold it and out. In. Hold it and out. Cis bonds, or sorry, not cis bonds, sigma bonds are stronger than pi bonds. Sometimes this is confusing because double bonds are stronger than single bonds. But if you think about it, a double bond is a sigma and a pi. So sigma bonds are stronger than pi bonds, but double bonds are stronger than single bonds because a double bond is a sigma and a pi together. Yes. Triple bonds are stronger because it's a sigma and a pi and another pi. So they're all additive. Okay? So counting them, let's just do one example and then we'll be done. Let's count our sigma bonds. 1, 2, 3, 4, 5, 6. And remember, when you have a double bond, that's going to be 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16 sigma bonds. Pi bonds. What color? Should we make them orange? Green, light green. There we go. 1, 2, 3. 3 pi bonds. Did you guys catch that? Yes? Okay. There's some exercises. These are your homework. And because there's not really much there, I would like you to memorize all the molecular geometries. Okay, so go and review your molecular geometries. Does anybody need a printout of the flashcard kind of thing? Yeah? Okay.